So good morning one and all. So in the previous month we have stopped at unit 3, that is deflection of beams by strain energy method. So just I'll brush up these things, then we can go with numerical with the frames. Okay. What we have done in deflection of beams by strain energy method, here we have studied with different conditions, that is strain energy due to axial load, strain energy due to flexural, and strain energy due to bending, that is flexural and shear stress. So three important derivations we have carried out. One is strain energy due to axial load. Okay. So second one we have done with strain energy due to bending. Strain energy due to bending. Third derivation we have done with energy stored in a body. So that is strain energy stored in a body. Strain energy stored in a body due to shear stress. Okay. To brush up the basic about what is strain energy, we know that every material has got deformation, which is elastic in nature, has got its deformation. So after removal of load, what happens is it regains its original shape. That is the quality of elastic materials. Whereas you compare with brittle materials, what happens? It fractures soon. So here what happens is, what is strain energy? Is work done in a stored body or a energy stored in a body, which helps to regain the original shape of that particular body, which is elongated upon the action of force. Okay, that whatever energy is stored in a body which will make a body to regain its original shape is called as strain energy, which will behave like a spring. Okay, so this strain energy you can find out due to axial load. We have taken a small bar, right? Then we have applied a load and we have derived what is the equation for this, that is it is W square by 2 AE into small l. Okay, strain energy due to axial load. Next we have done with strain energy due to bending. We have taken a flexural beam, right? Then we have taken a small elemental strip in that and we have derived a formula for that. It is integration of 0 to L m square divided by 2 EI into ds. That is strain energy stored in the entire beam due to flexure. Then we have done the derivation of strain energy stored in a body due to shear stress. Okay. Then we have come across virtual work, concept of virtual work. Then we have done with Clark-Maxwell theorem, reciprocal theorem. We have done with Castigliano's theorem, right? So all these basics we have already completed. Later I have started some numericals with cantilever with a point load, right? Then I have done with Udl case. Okay, in a point load what happens? Simple, I have solved the numerical with a point load taking 50 kilonewton or 100 kilonewton, whatever, simply supported, as well as cantilever. What you have to do is you have to treat this load as P, so that when you write the strain energy equation, dou m by dou P is integration of m square divided by 2 EI dx. So we have to have this derivative with respect to P. Okay, we are going to differentiate with respect to P. That is why that P term is taken. So load will represent as a P. Later at last you are equating P is equal to the load in the final substitution. So you will get what is strain energy in that system. Okay, this was the thing which we have done. We have done with cantilever, we have done with simply supported type of beam. Alright, we have replaced P. So derivative dou m by dou P derivative. Okay. Next we have done with Udl case, where we have taken Q as the imaginary load. Alright. So this was simply supported beam with Udl case. Okay. So it was some load with 10 kilonewton. We have taken an imaginary load Q. Okay. So that what is the importance of this taking Q is that will act as the imaginary load. Later we'll have derivative with respect to that. Okay, and later when you have differentiation with respect to Q, dou m by dou Q, so at last you are going to replace Q is equal to 0. Then put whatever P remains or the variable remains, there you are going to put the load. Okay, so P is represented at load there. So two things we have observed. One is UDL case, we have taken P as Q, both variables we have used P and Q. So in point load you have taken as P. So already I have explained this, so I will not repeat once again. So just practice these numericals, fine. With cantilever, different type of loading with in the cantilever and simply supported UDL case and point load case. Okay. One thing left was in this chapter is frames. So beams already we have completed with point load and UDL. The left part is frame, or it is called as bent cantilever. Okay. Numericals on deflection of beam are finding the strain energy deflection, that is vertical deflection as well as horizontal deflection in bent cantilevers. Okay. So one standard case I'll take so that we'll just clear how you are going to take vertical deflection and horizontal deflection. Later we'll have combination of horizontal and vertical deflection. Clear? So first numerical I'll solve with find the vertical deflection at point capital A of a bent cantilever by strain energy method. Okay. If I go simultaneously with horizontal as well as vertical loading, you get confused. So we'll have specific, we'll first deal with vertical deflection, then we'll go with horizontal deflection, then we'll have combination of that. So once I complete with standard case, I'll go with one numerical, one or two numericals. Later I'll solve with horizontal deflection, then we'll go with some numericals, then we can have combination of that. Okay. So we'll have a frame A, B, C. So this is a load P. So you need to find the deflection. Okay. So I'll take this as A and this as C. You have to find deflection at point A. Okay, vertical deflection at point A. So distance, this is small a, okay, for beam AB. For column BC we have height h. Okay. So moment of inertia of column is I as well as beam is I. Okay. So what you have to do? You have to cut a section in the column area or in the column length and take x distance from the beam. Okay. In beams, what we used to do is from support we used to cut a section and take x distance. Clear? So now what you have to do is, if you open this as the beam, it will be as same, right? So at point B and BC column, you are going to cut the section XX. Then you are taking x distance in beam section AB. Okay. So strain energy, we have equation integration of m square divided by 2EI dx. Okay. If you open it, it is 2m by 2e dou m by dou p dx. Okay. Ya is equal to integration of em by ei dou m by 2p dx. No need to split always. Once you write the strain energy is equal to integration of m square by 2ei dx, directly you can split and write the deflection at vertical deflection at A is integration of em by ei dou m by dou p dx. Okay. Next, we need to draw a table, that is, we have portion, we have origin, then we have to find bending moment at section XX, then we have differentiation with respect to P, we have limits, and we have moment of inertia I. Okay. So there are two portions, AB, right, and BC. AB and BC, two portions. So for AB the origin is A, for BC the origin is B. The first alphabet stands as the origin. Okay, for AB portion, if you take AB, this will be the origin, and if you take BC as the portion, B will be the origin. Okay, first alphabet stands as the origin. Bending moment at XX for AB section, AB amid this section, your moment about A or in this section will be P into X. It is P into X. Okay. If you take BC portion, it will be P into A. Correct? A as the origin, moment about A will be P into X. Alright? Moment about B or in BC portion will be P into A. Clear? Differentiation with respect to P. So what remains here? X. Here with respect to P it is 1. A remains. Okay. Limits will be 0 to A and this is 0 to small h. So moment of inertia is I and I. We are not going to vary. We are keeping it same. Alright. Now I'll use this equation. This is strain energy is integration of m by EI dou m by dou P dx. Okay. So vertical deflection 1 by EI I'll take outside. Okay. 0 to A first portion 0 to A. Okay. Bending moment at x-axis P into X into dou m by dou P is X dx plus integration of 0 to H. So for BC portion it is P into A and dou m by dou P is small a dx. Clear? Shall I repeat once again? Strain energy is integration of m by EI dou m by dou P dx. Clear? So first AB portion bending moment X is P into X. Okay, m by EI moment is P into X. Derivative with respect to P is X. Okay, the second term, the integration from 0 to H, right? Moment m by EI is P into A and differentiation with respect to P is small a. Just solve it, it will be vertical deflection YA is equal to 1 by EI in bracket P x square divided by only P x square. Okay, P x square dx integration of 0 to A plus 0 to H integration P into A square dx. Okay. So 1 by EI integration of x square is x cube by 3 P into x cube by 3. Limit is 0 to A plus P A square integration of with this remains is x variable. Okay, dx h. Limit will be 0 to small h. Okay, so total vertical deflection will be P A cube by 3 EI plus P A square h by EI. This is the equation which you get it for vertical deflection. Next we'll move with horizontal deflection. This is about vertical deflection where you are going to draw this table and pose the limits 0 to A, 0 to H and find out vertical deflection at A point. Next standard derivation is we are going to find horizontal deflection at point A. This is only with respect to vertical deflection. Once I finish with the standard cases, then we'll go with some numericals with point load, vertical and horizontal later. Okay. So what I'll do, I'll find the horizontal deflection now. Okay. To find the horizontal deflection at point A using of a bent cantilever using strain energy method. Okay, the figure remains same. All right. So this P will be vertical load as same as your vertical deflection. But one thing is, I'll take the horizontal deflection as Q, because I am going to find horizontal deflection. I need horizontal load. Clear? For vertical load, you cannot get horizontal deflection. So P remains as it is. We have to take some imaginary load, imaginary force Q at point A. Okay. I'll write a reason here why we have to take Q. Since we have to find the horizontal deflection, okay, since we have to find horizontal deflection at point A, comma, but there is no horizontal force acting at point A, full point. Hence, imagine a imaginary force horizontal force Q as shown in figure. Now you can clearly understand what I am going to do is, since we are finding horizontal deflection, okay, there was no horizontal force given in the question, it was only vertical force P. What I am doing is, since we have to find horizontal deflection at point A and there is no horizontal force acting at point A, hence we have to imagine a horizontal force Q at point A, so that with respect to Q we'll have the horizontal deflection. With respect to Q we can find what is the horizontal deflection. Okay. So strain energy by A will be integration of m by EI, okay, dou m by dou Q dx. Okay. So how you get this is same thing. Strain energy is integration of m square divided by 2 EI dx. So horizontal deflection YA or the vertical deflection whatever, with respect to Q will be integration of 2m by 2 EI dou m by dou Q dx. Okay. Later you get this equation. 2 get cancels. You get y is equal to integration of m by EI dou m by dou Q dx. So with respect to Q you have to travel. Alright. So this is very important. Clear? So I'll just put a table now. Okay. So once the table is formed, just the left part is you have to insert in a formula and get what is horizontal deflection. Okay. So we have portion, okay, we have origin, we have bending moment mxx, then derivative with respect to Q, not with respect to P. If you are doing with respect to P, you are going to get vertical deflection. If you are going to do with respect to Q, you are going to get horizontal deflection. Okay. So differentiation with respect to Q, then comes limits, then moment of inertia I. Okay. The portion remains same, AB, BC, right? AB and BC. The origin of portion AB will be A, for BC will be B, because first alphabet stands with the origin. Next, bending moment with respect to X, taking A as the origin. So what it will be? It is P into X. Okay. Next, bending moment or moment about B. Okay, it will be P into A plus Q into X. P into A plus Q into X. It will be moment about B point. Okay, so this is your B. So P into A, Q into X. Alright. So in the first term, AB, you don't have Q variable. So differentiation with respect to Q, nothing left. It is 0. Okay. Limit here it is 0 to small a, and this remains with moment of inertia I as usual. Next, differentiation with respect to Q, the second term, you get only X. Okay. And limit is 0 to H. This is I. Okay. So once again I'll repeat. You have got two portion A, B, B, C. The first alphabet stands as the origin. Here A as the origin and here B as the origin. Moment about A will be P into X, will be moment about A. Moment about B will be P into A, Q into X. Next, find out differentiation with respect to Q. Here you don't have Q variable, so nothing is there, 0. Here it is X. Okay, this becomes 1 and X remains. Limits are 0 to A, 0 to H, because this is H and this is A. Moment of inertia I have not varied, again I have kept it as I. Okay. So put in this equation, okay, all these parameters. It is integration of 0 to A, okay, for AB section. So moment is P into X. Okay, dou M by dou Q, it is 0. Anything into 0 is 0. So even though this term you cannot solve, everything is 0 here. Plus plus 1 by EI. So second term is P into A plus Q into X. Right. So it is integration of 0 to H. So you have second term P into A plus Q into H. Okay, that is the bending moment equation. P into A plus Q into X. Then derivative with respect to Q is X. So you have X here into dx. Okay. So first term you have derivative 0. So anything into 0 is 0. So no need of solving first term. It is everything 0. So it is 0. So directly we have 1 by EI. Okay. It is 0 plus 1 by EI. Okay. So just solve this term. What we get here, 0 to H P A X plus Q into X square dx. Alright, just multiply this. P into A into X, Q into X square dx. Okay. So it is 1 by EI. Okay. P A X, integration of X is X square by 2. X square by 2 plus Q into integration of X square is X cube by 3. Limit 0 to H. Okay. Ultimately what remains? 1 by EI. Okay. Wherever X you find, you put it as H. You get P into A H square by 2 plus Q into H cube by 3. Okay. So ultimately what you have to do is you have to put Q is equal to 0, so that you get horizontal deflection. So at end what you have to do is put Q is equal to 0. Here you put Q is equal to 0. What remains is dou U by dou Q is P into A into H square divided by 2EI. Clear? This is how you have to find horizontal deflection. For vertical deflection, no need to have any force, any vertical force, because already it is defined as P. Okay, once it is defined as P, you have to take derivative with respect to P and continue the process. If it is asked as horizontal deflection, okay, you should have one horizontal force in a question, or else you have to assume some horizontal force Q. Okay, so that at last when you are putting Q is equal to 0, you find the horizontal deflection equation. So with this, what we'll do is we'll have one numerical on the vertical deflection, okay, or you can have with horizontal, whichever. So we'll have first with vertical, next you can have with horizontal, both you can try, right? One numerical I'll just solve. So first numerical, I'll go with point load. Okay. So directly we'll have find vertical deflection at point A using strain energy method. Okay. So first we will solve with point load so that will be easy for us to carry out horizontal as well as the combination. Okay. So this is the numerical. I am taking a simple 50 kilonewton force. This is A, B, C. So this is distance with AB is 2 meter. Distance with BC is 4 meter. Okay. So we have to find what is vertical deflection here. Vertical deflection at point A. So here what you have to do is replace this load with P. Take this as P. So that when you are going with differentiation with respect to P, the terms will come into account. Later at last, the variable P is replaced with 50 kilonewton force. So no need to take any imaginary load here because there are no, they are not asking any other deflection, no horizontal deflection. Okay, only purely it is asked with vertical deflection. What is the first step? We have to divide the section, okay, XX, and take X distance from beam AB. Okay. Then you can apply the strain energy formulas. It is integration of m square divided by 2EI dx. It is integration of 2m by 2EI dou m by dou p dx. Okay. So dou u by dou p is m by EI dou m by dou p dx. Okay. So these are the basic equations we need to write at the initial part before drawing the table, right? Because we should have this equation integration of m by EI dou m by dou p dx. Clear? Next we'll have a table with portion. We have origin. We have bending moment or movement at section XX, whatever. You can take mxx or you can say bending moment at xx. Okay. Next, differentiation with respect to P, dou m by dou P. Then you have limits. Then you have moment of inertia. Okay. Portion and origin remain same because we have only two sections A, B, B, C. Okay. We have portion A, B, B, C. First alphabet stand as the origin. Okay. A as the origin and B as the origin. Okay. Next, bending moment at section A. You have to take moment about A. What is that moment? It is P into X. Don't take 50 kilonewton because we need to have differentiation with respect to P. Later at last you can put P is equal to 50 kilonewton. Now it is not required to take 50 because once if you take P 50 here 50 into X, you cannot have differentiation part with respect to P. So let it be the variable P into X. Next we have moment about B. It is P into 2. Okay. So P into 2 and this is P into X. Moment about A is P into X, B is P into 2. Differentiation with respect to P is X, differentiation with respect to here it is 2. Okay. Differentiation with respect to P, it is 2 remains here and X remains here. So limit here it is 0 to 2, moment of inertia is I, it is 0 to 4 and moment of inertia I. Then we'll have this equation and replace all the parameters. You have dou U by dou P is integration of M by EI dou M by dou P dx. Okay. So it is integration of 0 to 2. So first term will take AB, the limit is 0 to 2, moment is P into X and the derivative is dx. Okay, I'll put one bracket. Okay, moment is P into X and differentiation with respect to P is X dx plus second term it is 0 to 4, second limit, moment about BC is P into 2 and differentiation with respect to P is 2 dx. Okay, these are the two terms of AB span and BC span. Okay, next what remains is equal to. Okay, so I'll take P by EI constant, I'll take outside. So what remains here is X into X remains X square. Okay, integration of 0 to 2 X square dx plus, so P already I have taken outside, P by A it is 2 to the 4P. Okay, 4P by EI and it is X, it is integration 0 to 4 X. Clear? So P by EI I'll take outside, let it be EI with respect to EI. Here 2 to the 4P by EI I'll take outside, X remains inside. Okay, integration 0 to 4, here it is integration 0 to 2. Next P by EI, okay, integration of X square is X cube by 3, limit 0 to 2 plus 4P by EI, integration of X is X square by 2, limit upper limit 4, lower limit 0. Okay, no, this is directly X, not X square, dx is X. Okay, so we have P by EI, just put X, it is 2 cube by 3 plus 4P by EI, X is 4 inside. Okay, we have 2 cube, go to the 8P by 3 EI plus 4 for the 16P by EI. Okay, so replace P is equal to 50 kilonewton at this stage now. Okay, so P is 50, now replace P is equal to 50 at this stage. What remains? We have, shall I rub this? 8P, what remains? 8P divided by 3 EI plus 16P by EI. So this is the strain energy dou U by dou P. Now you are going to replace P as 50 kilonewton. It is 8 into 50 by 3 EI plus 16 into 50 by EI. So this will be 133.33 by EI plus 800 by EI. So ultimately you get strain energy as 933.33 divided by EI. Clear? So what we have done? Initially a vertical deflection. To find vertical deflection for vertical load we have taken a variable as P, not a load. Okay, we have taken a P so that we could have differentiation with respect to P. The variable should remain there. Then those terms are introduced or replaced in strain energy formula, that is integration of m by ei dou m by dou p dx. Okay, first bending moment term with its derivative of portion AB, second term portion BC with its derivative and with its moment, then integrating the parts, both the sections. Then at last you are going to replace P with 50 kilonewton because that is the vertical load. Ultimately we get the deflection or the strain energy deflection 933.33 by EI at point A. Okay, this is a simple numerical where we have done with the point load of 50 kilonewton. Okay. Next we'll have both horizontal and vertical deflection. Okay. Now I've done only with vertical deflection. Next we'll have both horizontal and vertical deflection with point load. We'll stick up with point load. Later we'll have combination of UDL and point load. Okay. So what I'll do is I'll take a point load with horizontal and vertical both. Okay, shall I change the question? We'll have find horizontal and vertical displacement or deflection. Find horizontal and vertical deflection. Okay, at point C you can say now. So I have changed the nomenclature at point C using strain energy method. Using strain energy method for bent cantilever beam as shown in the figure. As shown in the figure. Okay. So we have Young's modulus E is equal to 200 into 10 power 6 kilonewton per meter square and moment of inertia is 40 into 10 power 6 minus 6 meter raised to 4. No need to convert the unit because it is in kilonewton and meter. So we'll stick up with this because load is in kilonewton and distance is in meter. So no need to change any unit in E and I. So that is standard. It is fixed because it is in kilonewton and meter. So no need to worry about that. So numerical is the bent cantilever. I have taken this as A, this as B, this as C. Okay. So vertical load is given at point C. It is 4 kilonewton. Okay. And moment of inertia for BC section is I. For AB section is 2I. Height of the column is 6 meter and width of this is 4 meter. Okay. What is the first step? First and foremost step. To have a section, we need to cut a section. Okay. So we need to cut a section for BA. So I'll have the section XX and distance X from the beam BC. Okay. So what is going to ask? He is asking you to find horizontal and vertical deflection both. So we have vertical load. Of course, we'll get vertical deflection. To have horizontal deflection, we should have an imaginary force Q. This is what the change takes place. To find horizontal deflection. Okay. So Q is imaginary horizontal force. Okay, because we need to have horizontal deflection as well as vertical deflection at point C. Vertical load is there, we'll get vertical deflection. But about horizontal deflection, we don't have horizontal force, that we need to assume it as Q. That is a change. What we have done in standard cases, same thing, the same procedure we are following. Alright. So first we'll go with finding horizontal deflection. Then we'll have with vertical deflection. Okay. First is we are going to find horizontal deflection. So already equation is known because I'll not write the equation again and again. So we have equation, it is strain energy dou m by dou p. Okay. So since we are finding horizontal deflection, we'll make it as q. We'll stick up with our own variable. Dou m by dou q is integration of em by ei dou m by dou q dx, because this is q force. Okay, not p. Vertical comes, then you have to take p. Okay. So directly we'll have a table, portion, we have origin, we have moment about xx, we have dou m by dou q, derivative with respect to q or differentiation with respect to q. Next we have limits. Next we have moment of inertia I. So portion will be here CB. Okay, because terms have changed. I have not taken it as ABC. I have taken it as AB reverse. So first beam section CB. Right. Next we have BA, column BA. So first alphabet stand as the origin. Here C is the origin. Here B is the origin. Okay. We are finding horizontal deflection. So moment about xx in CB portion, what it will be? It is 4 into x, moment about C, 4 into x. Okay. So this is 4 kilonewton vertical force into its perpendicular distance, 4 into x. Okay. Next, moment about BA in this section you have to take. It will be 4 into 4, alright, plus q into x, q into x, 4 into 4 plus q into x. So always in horizontal, when you are finding horizontal deflection, first span will lead to 0 because you don't have q variable, you don't find q variable, so derivative will be 0 here. So that is one shortcut way to have this solution. Okay, differentiation with respect to q, you don't have q variable here, it is 0, limits will be 0 to 4, moment of inertia I. Next, differentiation with respect to q, here x remains. Okay, you have limit 0 to 6, it is 0 to 4 meter and this is 0 to 6 meter. So moment of inertia is 2I. Just concentrate on this because sometimes it will be 2I, 3I. Okay, if you take only 1 by A and continue, this may go wrong. So concentrate more on I. Next, dou u by dou q is 1 by EI. Okay, I am taking first section 1 by EI. Integration 0 to 4. Okay, you have 4 into x moment. 4 into x, differentiation value is 0. Dx plus 0 to 6. Second span BA, it is 0 to 6 limit. So we have 1 by 2 EI. Okay, moment is suppose 16 plus qx, 16 plus q into x dx. Okay, into x dx. The first term is 0, anything into 0 is 0, so this get vanish. Differentiation with respect to q is 0 plus integration 0 to 6, 1 by 2 EI. Okay, it is 16 into x plus q into x square dx. Clear? 16 into x plus q into x square dx. So dou u by dou q, this is already 0. What is left? 1 by 2 EI. Integration of x is x square by 2 plus integration of x square is x cube by 3. Limit 0 to 6. Okay. So it is 1 by 2 EI. 16x is 6 square divided by 2 plus q. X is 6 cube divided by 3. Okay. Now this is a stage where you have to put q is equal to 0. Okay. This is a point where you have to put Q is equal to 0. So this entire terms get vanished. Okay, Q is 0, 0 into 6 cube, everything gets 0. Only left is 16 into 6 square divided by 2. Okay, 16 into 6 square divided by 2, okay, divided by 2 EI. So ultimately you get 144 by EI. If you solve this term, you get 144 by EI. Okay, E into I. So if you multiply E into I, you will have 8000 kilonewton meter square. Clear? If you multiply 200 to 10 power 6 into 40 into 10 power minus 6 will be 8000 kilonewton meter square. So I'll divide 144 by 8000. 144 by 8000 will be 0.018 meters. Okay, meter. So this is about horizontal deflection. Clear? So what you have to do? You have to take a Q as an imaginary horizontal force, assume it as at point C. Clear? Then strain energy with respect to Q, draw a table, find out the limits, then put these limits, these values of moment, derivative, point, then solve it. At last put Q is equal to 0 because we don't know what is that horizontal force. So it is replaced as 0. You get horizontal deflection as 0.018 meter. Okay. Next remaining is we need to find vertical deflection. Okay. Next is vertical deflection. Okay. So Q will not play any role here. So I'll just rub it. Okay. Q is not going to play any role. Only you have to find the vertical deflection at point C due to vertical load 4 kilonewton. So 4 kilonewton is replaced as P. So that we have to go with derivative of with respect to P, right? I'll draw a table, portion, alright, we have origin, movement about xx, okay, bending moment xx, derivative with respect to P, we have limits, we have moment of inertia I, okay. So portion remains same, CB, BA, so nothing change in portion, CB, BA. The first alphabet stands as the origin, CB. Moment about XX about point A is P into X, alright. Moment about point B will be P into 4, don't take 4 into 4, later we'll replace P with 4, it will be P into 4. So P into 4, so derivative with respect to P is X, derivative with respect to P is 4 here, limit it is 0 to 4, it is 0 to 6, this is I, this is 2I, okay. For beam it is I and for column it is moment of inertia is 2I, okay. Then we'll have strain energy equation, so it is dou U by dou P is equal to integration of m by EI dou m by dou P dx. So we'll replace all these terms CB and BA and we'll find what is the vertical deflection. Alright. So we have dou U by dou P is 1 by EI. So first term CB it is 0 to 4. Moment equation is P into X. Differentiation with respect to P is X dx plus second term 0 to 6. Bending moment is P into 4 and derivative is 4 dx. Alright. So dou U by dou P is equal to 1 by EI. Okay. So it is P into X square P into x square dx. So integration is 0 to 4 still, plus 0 to 6, 4 4s are 16p, alright. What remains? 16p dx. Okay. Next, 1 by ei, integration of x square is x cube by 3, it is 0 to 4, plus here what remains? 16p into x, 0 to 6. Okay. So it is 1 by ei p into 4 cube divided by 3 plus 16 into p into 6. Okay. After this, you are going to replace, put P is equal to 4 kilonewton. Now you can replace P with 4 kilonewton. Until there you don't replace, because you have to carry out this step with integration part. After integration, put the limits. After putting limit, you have to come back and replace P with 4 kilonewton. It is 1 by ei. So in bracket it is 4 into 4 cube by 3 plus 16 into 4 into 6. Okay, correct? 16 into 4 into 6. So after solving this, you get 277.33 divided by ei. If you do e into I, the product of ei will be 8000 kilonewton meter square. Okay, I think I had written that. It is 8000 kilonewton meter square. So divided by 8000, you get 0.0346 meter. So this is about vertical deflection. So we have done a standard case with vertical, with horizontal, right? And I have taken a numerical on vertical. Then I have taken on horizontal as well as vertical. I think one numerical is remaining with the combination of UDL and the point load. So tomorrow I can take this and start with arches and cables. Fine. So the thing is, if you are going to find horizontal deflection, you have to take imaginary load Q, then solve it, have derivative with respect to Q, then later replace Q is equal to 0. If vertical deflection is asked for vertical load, you replace it as P variable and have the derivative with respect to P. Then you put all these terms in the strain energy equation. At end you can replace P with the load given in the question. You get vertical deflection. This is how you have to find horizontal and vertical deflection in bent cantilever beams. So one numerical tomorrow I am going to take with UDL and combination of UDL and point load. So after finishing this, we can have the arches and cables.